Hello friends, today I am here to discuss mechanical properties of materials. It is a part of strength of material syllabus. Of 10 properties I will discuss 5 properties today, and in next lecture I will discuss the rest 5. I am Manoranjan Kumar, lecturer in mechanical engineering, and I have done my BTech from NIT Jamshedpur. So we will start with the lecture. How the mechanical property is described. Mechanical property is described how material respond to the external force. If it is an object and if we are applying forces to it, how this material will mm, how this force will affect the internal molecules and atoms of the material, how what changes will occur in the material, will there be any permanent deformation to the material or it will break, what will be the limiting force that it will lead to the fracture. All these are discussed in the mechanical properties. Mechanical properties are very much important in engineering, material selection, mining and construction, as different material behave differently upon the upon action of the forces, external forces. So we'll move to the first property, that is elasticity. Elasticity is the ability of material to regain to its original shape after force is removed. If it is an object and we are applying tensile force to it, obviously there will be change in the length of the material. There will be change in the length of the material, and if once the force is removed, if the material returns back to its original shape and size, that property is known as elasticity. It is a ability to regain its original shape after force removal. Best example, we can have rubber band. Once we stretch the rubber band and leave, after that the rubber will come back to its original shape. Same is with a steel spring. If we compress or stretch the steel spring, and once the force is removed, the spring comes back to its original shape and size. This property is the elasticity. And there is a term elastic limit. It is a limit to the stress, that is that maximum stress that we can apply up to which the material will come back to its original shape. Once the elastic limit is crossed, the material does not return to its original shape and size. So elastic limit is the maximum stress for the complete recovery. Up to the elastic limit, we can have the recovery of the material to its original shape and size. We can see from an animation. Uh, It is a spring. If we apply 100 kg of the weight and then if we remove, we can see regaining of the shape and size of the spring. And this is the stress strain diagram. It is stress is on the y-axis and strain is on the x-axis. If you are applying force, if you are applying force, mm, there will be increment in the stress, and corresponding to that there will be change in the length. So we will have a corresponding stress to a stress. Our input is the stress and out we are get the change we are getting is the strain. So up to a proportional limit, the stress strain, that Hooke's law is valid. We will study in later classes what the Hooke's law state. The proportional limit. After that, we get the elastic limit. This is the limit up to which there is a recovery of the material. Once the force is, or a stress is removed, the material will regain its original shape and size. We will move to the next property, that is the plasticity. Plasticity is the next step of the elasticity. Means in It is the ability to retain permanent deformation after removal of the force. In early slide, I told you if you are applying a force and if we get back the original shape and size, that property is the elasticity. But upon removal of the force, if you don't get the original shape and it retains the permanent deformation, there is a permanent deformation in the material. Such property is called the plasticity. Even if we are removing force F, even if we are removing the application of force F, we don't get the original shape and size. There is a permanent deformation in the material. We can have the example of clay modeling. Once we mold the clay, we don't get back the original shape of the clay. Metal forging there are many application of plasticity in metal forging industry. There is a complete permanent deformation and complete change of the property of the material on the application of force. There will be complete change in the shape, size. It is used in forming, stamping, metal shaping. We'll see from the animation. See, without plasticity, when the force is removed, when the twisting force is removed, it is getting back to its original shape. But with plasticity, even if the force is removed, twisting moment is removed, the material doesn't get to its original shape and size. We can have another. You can see the roller. As the roller is moving over the sheet, there is a complete deformation, the complete change in the thickness of the sheet. This is the plasticity. This is due to the property of plasticity. Next, we will go to the next property, that is the rigidity. Rigidity is the resistance to deformation. If you want to give a change to something, there will be a resistance. That resistance is the rigidity. Resistance to deformation under applied force is the rigidity. Higher the rigidity, higher will be the resistance to deformation. Means I want to make a change in anything, but there will be resistance from other side. The higher the resistance, higher will be the rigidity. We can have example from steel band and fine ceramic. I'll show you the next slide. Uh, Higher modulus of rigidity means more stiffness. There will be more stiffness if we have higher modulus of rigidity. We will show you through an animation. Uh, you can see this is the alumina of fine ceramic and this is the stainless steel. If we are applying load on stainless steel, there is much more deformation as compared to the fine ceramic. It means fine ceramics is having much higher rigidity compared to the stainless steel. So higher the rigidity, higher will be the resistance. So fine ceramics is having higher rigidity and metal is having lower rigidity. We'll move to the next property, that is the ductility. Ductility is the property of material to be drawn into wires without breaking. It shouldn't break. If we are if it is object and if we are applying force, if it is drawn into wire, this property is known as ductility. We can have example of copper wire, gold wire. These are the example of ductile material. How it is measured? It is measured by the elongation percent. How much there is a change in the length? How much percentage the length has changed? Or how much there is a reduction in the cross sectional area? This is the cross sectional area. The cross sectional area will reduce upon the upon once it is changed to wire. So in ductile material, in ductility, it is ability to be drawn into wire without breaking. We'll see from the GIF animation. You can see we are applying force on it, and there is thus this rod is being changed, elongated, and there is a change in the cross section. The cross section area is reducing and length is increasing. We'll move to malleability. Malleability is the ability to be hammered or rolled into thin sheet, just opposite of ductility. In ductility, we were converting into thin wire. Here, we are converting into thin sheet. In ductility, there was change in the length, but in malleability, there will be change in the area. No, a best example we can have aluminum foil, gold leaf. The difference in how it is different from mobility, there is a difference due to the direction of the deformation. It is along the axis. It is in the lateral direction, planar direction. In malleability, we will have change in planar direction. We can see from the animation. See this metal thick plate is going through the roller and it is being reduced in the thickness and coming out as a thin sheet. This is the best example of the malleability. Thank you. We'll discuss rest 5 in next lecture.